Hello everyone and welcome to our calculus notes for section 5.5. Today we're talking about exponential functions where the base is not e. So we're going to get into some properties and laws here. The first one is a definition of exponential function to base a. So if we have an a to the x function, we can rewrite this as a base e by writing e to the natural log of a times x. Now the laws of exponents should all be reviewed here. So a to the 0 power is 1. If we multiply like bases, that means that we add their exponents here. If we divide like bases, that means we subtract the exponents. And if we raise an exponent to another power, that means we multiply the exponents. Now here's the definition of logarithmic function to base a. So log base a of x equals 1 over the natural log of a times the natural log of x. And we might also see this as the natural log of x over the natural log of a. So this is how you can convert a logarithm in any base into the natural log function. Now, some logarithmic properties. Log base a of 1 is going to equal 0. Log base a of x times y equals log base a of x plus log base a of y. So that's very similar to the natural log property that we were looking at before. Log base a of x to the n equals n times log base a of x. So again, that's the same also. So we just bring that n out in front. And then log base a of x over y is log base a of x minus log base a of y. And that's the same thing there too. When you divide, we end up subtracting. Now some properties of inverse functions. If we have y equals a to the x, this is true if and only if x equals log base a of y. Okay, so we're going to use these in solving some equations involving bases other than e. We also know a to the log base a of x equals x. Okay, so if you have the a as your base in both places here, then all we're going to be left with is x. And also, if we have log base a of a to the x, that's also just going to equal x. So this part right here essentially cancels out, and we're just left with x. All right, so let's try some examples now. Here it says, solve for x. And so we have all of these tools at our disposal as we're trying to solve this. So if we have something 3 to the power of x and it equals a number, what we're going to do is actually use this idea right here to be able to get that x by itself. So you can see that x is the exponent. And so what we're going to do is we're going to take log base 3 of both sides. Okay, so we have the log base 3 of 3 to the x equals the log base 3 of 1 over 81. Okay, so here log base 3 of 3 to the x is just going to equal x. And now what we want to try to do is rewrite this as a power of something to the third. Okay, and it turns out that 81 equals 3 to the 4th power. So we can rewrite this here as log base 3 of 3 to the negative 4th power. And it's negative 4 because the 81 was in the denominator. And now we see the same idea playing out right here. Log base a of a to the x equals x. And so log base 3 of 3 to the negative 4 is just going to equal negative 4. All right, in letter B, here we have log base 2 of x equals negative 4. So in this case, we want to think, how can we get rid of a log base 2? Well, in this case, I'm going to look at this property right here. Okay, so if we take a to the log base a of x, that just equals x. So what we want to do is raise both of these as the exponents of a base 2. So we're going to write 2 to the log base 2 of x equals 2 to the negative 4th power. Okay, so if you ever want to get rid of the log base, okay, take that base and raise it to that power. So here, the 2 to the log base 2 of x turns into x, and here we have 2 to the negative 4th, which is 1 over 2 to the 4th, which is 16. Okay, in letter C here we have the log base 5 of 25 equals x. Now in this case, we already have a log and a 5, and it looks very similar to this one right here, log base a of a to the x, except here we have a 25 instead of an a to the x. So what we're going to do is try to rewrite 25 as a as 5 to some power. Okay, and we know that 25 is 5 squared, so we're going to rewrite this as log base 5 of 5 squared equals x. And now we know log base 5 of 5 squared is just 2. So in this case, x equals 2. Okay, so that's how you use some of the properties of logarithms to help solve equations. Well, let's move on. Next, we're going to talk about differentiation for bases other than e. Okay, so here we have the derivative with respect to x of a to the u power. So instead of e, this is a different base, it's a. And what it is, it's going to be the natural log of a times a to the u du. Okay, so the only difference now is that we multiply by the natural log of a. And this is really what we were doing with e. So if we think about it, if we have the derivative with respect to x of e to the x, if we followed the same pattern here, we would get natural log of e times e to the x. Okay, but what is the natural log of e? Well, that equals 1. So 1 e to the x, and so we were just left with e to the x. So it was a special case of using this formula. So now we just have to remember to put the natural log of a multiplied by a to the u power. Okay, let's give that a try here with these two examples. So in these examples, we do want to determine what a is, and this is our base. So here the base is 2. And then for u, we're still going to let u be the exponent. So here u is x, and then du is just going to be 1. And when we're finding derivatives, we don't really have to write dx here, because the derivative of x is also just 1. And so don't worry about putting the dx down there. Okay, so let's follow our pattern to find our derivative now. So it's going to be the natural log of a, or the natural log of 2, times a to the u, so 2 to the x, times the derivative of u, which in this case is just 1, and so we would just leave it here as our final answer. In letter B, a is going to equal 2, and now u is the function 3x, and so du is going to equal 3. So if we apply our derivative, so f prime of x is going to equal the natural log of a, so the natural log of 2, times 2 to the u, or 2 to the 3x, times the derivative of 3x, which is just 3. And we probably would rewrite this as 3 natural log of 2 times 2 to the 3x. Now this one kind of has an interesting side note. If we had used one of the properties, we could have changed 2 to the 3x into 2 to the third raised to the x power. And if we had done that, then we would have gotten 2 to the third is 8, and this would have been 8 to the x. And in this case, f prime of x would have been natural log of 8 times 8 to the x. And it turns out, what's interesting, these would actually be equal to each other. Alright, so that is the fun, because we can get different answers depending on how we started the process. Okay, so I would accept either one of these as being correct. All right, in our next examples here, we're going to be using this derivative form. Okay, so the derivative with respect to x of log base a of u is 1 over the natural log of a times u du. Now, you might also want to think about this as u prime over natural log of a times u. Okay, and this is very much related to what we were doing with the natural log. So you'll remember the derivative with respect to x of the natural log of u was just u prime over u. And so again, all we have, if we were going to use the same process, is the natural log of e times u. And then it would be the same thing. But again, what is the natural log of e? It's just 1, and so it doesn't really factor into our equation. But all along, this is really what we were doing. Okay, so now we just got to add in that natural log of a because our base changes. Okay, so again, we need to identify what our base is. In this case, it's 10. And we're going to let u be cosine x. And we're going to let du equal negative sine x. Okay, so let's go ahead and use this u prime over natural log of a times u. So u prime, so the f prime of x is going to equal u prime, or negative sine x, divided by the natural log of a, so the natural log of 10, times u, which is cosine x. Now in this case, if you have a sine x over cosine x, we might want to change that to tangent x. So we could rewrite this as the negative tangent x over natural log of 10. All right. Now in example D, here we have log base 2 of x cubed over 2x squared minus 1. And because we have a division here, we can use our properties of logs. And so we want to rewrite this actually as log base 2 of x cubed minus log base 2 of 2x squared minus 1. Okay, and there's only one other thing that we can do with our properties, and that's the 3 right here. We can move out in front, so this really equals 3 times the log base 2 of x minus the log base 2 of 2x squared minus 1. Okay, and in this case, a is going to equal 2, u is x, and du is just 1. In this case over here, a is going to equal 2, u is going to equal 2x squared minus 1, and then du will equal 4x. So if we find our derivative now, we're going to get u prime over natural log of a times u. So u prime is just 1, and we still have the 3 there. So we'll have 3 over natural log of 2 times u, which is just x. And then we have a minus right here. And so we're going to do u prime over natural log of a times u. So here u prime is 4x. And then we have the natural log of a, which is 2, times u, which is 2x squared minus 1. Now looking at this, we can actually subtract them if we got a common denominator. So most likely you're going to see answers with a common denominator. So let's see, we're going to need to multiply here by some factors. So here we have natural log of 2 and an x. Here we have natural log of 2 and a 2x squared minus 1. So the one on the left is going to need a 2x squared minus 1. So we multiply top and bottom here. And then the one on the right just needs an x. Okay, so our common denominator, let's go ahead and multiply here. So we're going to have x times 2x squared, which is 2x cubed, and then x times negative 1, so minus x. And this is going to be times the natural log of 2. Okay, and then here we're going to get 3 times 2x squared, so 6x squared. And then 3 times negative 1, which is minus 3. And here we have 4x times x, which is 4x squared. And remember, we have subtraction here, so we're going to subtract that, which equals 2x squared minus 3 over 2x cubed minus x times the natural log of 2. And there's our final answer. Okay, so make sure you apply your properties of logs here and then differentiate and put them as a combined fraction here. All right, let's try example E. Here we have 2 to the negative x power times cosine pi x. So here we do have a power, okay, but we're also seeing a multiplication. And so here we are going to have to use the product rule. All right, so let's apply the product rule here. So we have f prime of x equals our first function, 2 to the negative x, times the derivative of our second function. So the derivative of cosine is negative sine, but then the derivative of pi x is pi. So this is going to be negative pi sine of pi x, and then plus the second function, which is cosine of pi x, times the derivative of the first function. So the derivative of 2 to the negative x is going to be the natural log of 2 times 2 to the negative x times the derivative of negative x, which is just negative 1. Okay, and let's clean this up a bit. It looks like each of these have a factor of negative 1 and of 2 to the negative x. So let's pull out a negative 2 to the negative x. Okay, so here's the negative in all of those. And then here's the 2 to the negative x factor right there. And then what we're left with is going to be pi sine pi x and then plus, we'll move the natural log of 2 in front of this here. So the natural log of 2 times cosine pi x. And here's your final answer. Okay, so always be aware that the product rule and quotient rule are still in effect here. And that's how to differentiate with bases other than E.